Hello friends, I welcome you all to the next lecture of the JC eConnect series of online lectures. We are into module 4, that is design for shear. We are dealing with the calculation of the principal stresses generated due to the shear force in case of pre-stress members. Let us continue with the further examples. So, example number 4. In this example, we have a I section of area 55 into 10 raised to 3 mm square. The second moment of area, that is moment of inertia mi, is directly given in this example as 189 into 10 raised to 7 mm raised to 4, and the statical moment of area, that is A into y bar, is also given, which is 468 into 10 raised to 4 mm cube. The thickness of the web is mentioned as 50 mm. So pre-stressing forces are in the form of 25 wires of 5 mm diameter, and the stress applied is 900 Newton per mm square in each wire. For vertical pre-stressing, it is mentioned that there is a spacing of 150 mm center to center. We have to calculate the principal stresses at the centroid when a shear force of 80 kN acts on this section. Okay, so it's a practice example where luckily the details of the I section are given. So you can come across an example where only the dimensions of I section are given. You will have to calculate CG and MI. Okay, you have to locate the CG, calculate the value of moment of inertia, and then start with the example. So now it's up to your grip on the basics, whether you are comfortable in finding that portion and then going ahead with the example. So you need to practice it. So let's start with the concept of the example. Firstly, let us find the shear stress. We know the formula for shear stress is equal to tau v is given by V into S divided by I into B, where S is A into y bar. So directly we have the given values. The value of V, which is the shear force, is given as 80 into 10 raised to 3. The value of moment of inertia is given as 189 into 10 raised to 7. B, which is the width, which is 50, and we have the static moment about the centroid as 468 into 10 raised to 4. So going ahead with the calculations, we obtain a shear force of 3.95 Newton per mm square. Substituting B as 50, which is the thickness of the web, we get the shear stress as 3.95 Newton per mm square. Further, the horizontal pre-stress at the centroid is obtained by 24 is the number of wires, 19.7 is the area of 5 mm diameter bar into 900, which is the tensile strength in each wire, divided by the area of the section, which is 55 into 10 raised to 3 mm square. Hence, we get the horizontal pre-stress as 7.75. Next, vertical pre-stressing, again we get it as 19.7, which is the area, into 900, which is the stress, into divided by 150, which is the spacing for vertical members, into 50, which we get it as 2.46. Okay, then further we summarize here fx value to be 7.75, fy value to be 2.46, and fv, which is the tau v, which is the shear stress, as 3.95. So friends, there is a typing mistake here in the vertical pre-stressing. Please take that 200 as 900 in the calculation. Okay, because we have the tensile stress as 900. So maximum and minimal principal stresses, applying the formulas and substituting all the values, we get the stresses as 9.8 and 0.4, both are positive. That means the application of vertical pre-stressing, we are able to convert the tensile stresses into compressive stresses, and hence there are no tensile stresses existing. Both the values of the principal stresses, we get it as positive. So this is an example in which we have taken an I section and we have done the analysis. It's a simple example. Once again, when we get back to the classes, exactly how the pre-stressing is done, I'll explain you all. So now next example, I am dealing with the cantilever. Now it is a very nice example. Please listen to it carefully. Hope all of you are making the notes also as per the explanation. In this, a cantilever beam is given which has a cross section of 600 mm by 1650 mm deep. So it's a big girder of an concrete bridge. Span is 8 meters. It carries a reaction, means a point load at the far end. The intensity of the point load is given as 350 kilonewton. Means we have a cantilever beam of 600 by 1650, 8 meter span with a point load placed at the free end. It carries an UDL of 60 kilonewton per meter, including its self weight. So here we have an example of a cantilever beam carrying a UDL as well as a point load at its free end. The beam is pre-stressed by 7 cables, each carrying 1000 kilonewton force. 3 are located at 150 mm, 3 at 400, and 1 is located at 750 mm from the top edge. So directly the force is given, which is 1000 kilonewton, and the wires are distributed as per the given data. So let us start with the analysis. We have to calculate the magnitude of principal pre-stress at 550 depth from the top. So this is very important. Now here a particular depth is given at which we need to find the principal stresses. So firstly, let us find the value of y, that is the CG of the pre-stressing wires. So calculation goes like this. 3 number of wires are located at a distance of 150 plus 3 number of wires are located at a distance of 400 plus 1 wire is located at a distance of 550 divided by total number of wires. Here the area is not given as all the wires are of same diameter, and directly the pre-stressing force carried by each wire is mentioned in the example. So for calculating y, we can only take the number of wires and their distances which are in the given data. Therefore, calculating, we get the value of y as 343 mm. Further, eccentricity will be the center of concrete compared with the center of steel. So we got the location of steel as 343 mm, whereas the center of concrete will be at half of the depth of the section, which is 1650 divided by 2, which we get it as 825. Therefore, E is equal to 825 minus 343, which comes out to be 482 mm. Next, the pre-stressing force, we will get it as 7000 because we have 7 wires, each wire carrying 1000 kilonewton force. So 7 into 1000 is 7000 kilonewton, which is your pre-stressing force. Now, the moment due to the pre-stressing force will be given by P into E. Now this is the pre-stressing moment, which is an resisting moment, okay, which is an resisting moment. P into E, that is 7000 into 0.482, we get it as 3374 kilonewton meter. So this bending action because of the pre-stressing force will be acting as counterbalancing force for the bending due to the loads. So in the next step now, we have to use our basics to find the bending moment caused because of the given loading. So moment due to the external loads at the supports, as we have a UDL throughout the span and the point load which is placed at the end of the cantilever. The calculation goes like this. Point load is 350 over a span of 8 meters, that is 350 into 8, plus we get 60 into 64 divided by 2, that is nothing but W L square by 2. L is 8, L square is directly taken as 64. Please note down, again I am repeating, here the bending moment formula goes like this. P into L, P is the point load which is 350, which is placed at the tip of the cantilever, into L is the length which is 8 meters, plus the bending moment caused due to UDL in case of a cantilever beam is given by W into L by 2, that is nothing but W L square by 2. W is 60 whereas L is 8, so L square is 64. So directly we have taken 64 divided by 2, which gives out to be a bending moment of 4720 kilonewton. Okay, so this is the bending moment which is caused because of the loading, whereas in previous view we got the bending moment PE, which is the resisting bending moment which is developed due to the shear. Now here again your basics come into picture, and the calculations which we have done in the first chapter also become important in this example. Next, the maximum shear at the support, that is the reaction developed at the cantilever. As cantilever has a single support, the reaction developed will be 350, which is the point load, plus 60, which is the UDL over distance of 8 meter. So 350 plus 60 into 8, we get a reaction of 830 kilonewton. Then the value of I, BD cube by 12, we can calculate easily as 225 into 10 raised to 9 mm raised to 4. Therefore, now let's come on to the calculation at the depth of 550 mm from the top edge. Resultant direct stress tau V at 550 mm is equal to P by A plus P into E by I minus M into E by I. Okay, so resultant direct stress at what distance we are calculating here? 550 mm. P is nothing but 7000 into 10 raised to 3. Area is 600 into 1650. Then next we get moment PE 3374 into 275 divided by I minus the moment due to the external loads is M, which is 4720 kilonewton into 275 divided by 225 into 10 raised to 6. Okay, so here be careful, the value of Y which we are taking here is 275, which is 550 by 2. Okay, so here we are calculating the stresses at 550 mm from the top, hence the Y value is the center of 550. Okay, so we are getting the direct stress. This calculation we have done many times, that is the Fy value calculation in previous example. We have done it many times in the previous chapter. So we get the direct stresses at 550 mm as 5.43. So here 5.43 is our Fx value, which is your direct stress. Next, maximum shear stress, that is tau V at 550 will be given by V into IB multiplied by A into Y bar. So V is 830 into 10 raised to 3 divided by I is 225 into 10 raised to 9. B is 600 multiplied by area is 600 into 550 into 550 itself, because we have a well defined point at which we are calculating the stresses, which is 550. So here we get the shear stress as 1.1 Newton per mm square. Therefore, using a regular formula for calculation of maximum and minimum principal stresses, here there is no Fy, only Fx we have calculated as 5.43. Therefore fx by 2 plus or minus half into square root of fx square plus 4 times of tau v square, which we have got as 1.1. We get the compressive stresses as 5.65 and the tensile stress as minus 0.21 Newton per mm square. That means that as we don't have any vertical prestressing here in this case, we are finding that there is a tensile stress which is existing, which will result in shear cracks. Okay, so we find that here we have to resist this tensile force. So this ends the analysis examples. In the further examples, we will be going with the design for shear. Thank you.